Okay, here we go. So now we're going to talk about how free energy relates to equilibrium a little bit more. Now, the one thing we have talked about at this point, when we're at equilibrium, do you remember what delta G is equal to? 0, okay? Now, the first thing we've got to talk about here is the difference between delta G0 and delta G, which can be a little bit confusing, okay? But do you guys remember what this little symbol here stands for? Okay, it means we're at standard temperature, right? And standard conditions, really. So standard temperature, 1 atmosphere of pressure, okay? So 25 degrees Celsius, 1 atmosphere of pressure. If you just have a delta G, that might be at different conditions. So we might not be at standard temperature. Because remember, delta G changes when temperature changes, right? The spontaneity of the reaction gets influenced by whether the temperature is higher or lower. So when we're talking about delta G0, we're talking about a number that you can look up in the back of the book that will tell you what the delta G is for that reaction at standard conditions, okay? But just because we know the delta G at standard conditions doesn't mean that it can't change when the temperature changes. So we have an equation here that helps you to relate delta G to delta G0, okay? And again, this you can just look up in the book, or you can figure out using the data in the back of the book, okay? This we're going to have to calculate based on our conditions here, okay? So we're bringing back R, the ideal gas constant, but this one, because we're relating it to joules here, our R is going to be in joules per mole times Kelvin, okay, instead of the way that we've talked about the R most of the time in the past, which is the 0.0821 number, okay? T is what you think it is, it's absolute temperature, and then Q is the reaction quotient, okay? And so when we get equations in this unit, or in this, I guess, this section, we're going to have to actually figure out what is our reaction quotient here, okay? Now remember, the Q is, you find Q basically the same way that you find K, but it doesn't have to be at equilibrium for you to calculate Q, okay? So that's kind of the idea here. So let's just look at a sample problem here. Now, there's one kind of implied question that we have to think about in order to answer part B. But part A here says, write the chemical equation that defines the normal boiling point of liquid carbon tetrachloride, okay? So the normal boiling point is the temperature at which the pure liquid is in equilibrium. Okay, so we're talking about an equilibrium here. Okay, and if we've got CCl4 liquid, then at its normal boiling point, it's going to be in perfect equilibrium with CCl4 gas. Okay, so we're talking here about the temperature at which this thing is in perfect equilibrium. The delta S of the universe is going to be 0 for this process. Okay, the entropy is not increasing because this is an equilibrium, just at that one temperature. Okay, now at any other temperature, this reaction is going to be spontaneous in one of these two directions, right? So if it's above the normal boiling point, it's going to be spontaneous going this way, right? If it's below its boiling point, the reaction will be spontaneous going this way. Okay, that's kind of how that works. But right at this one temperature, we've got a perfect equilibrium happening here. Okay, now, at equilibrium, what is our delta G? Yeah, delta G is 0 at equilibrium, right? Okay, so when it says use thermodynamic data in Appendix C to estimate the normal boiling point of CCl4, what we kind of have to do here is we have to think about this equation, delta G equals delta H minus T times delta S, the equation that we learned the other day, okay? Now we just said at equilibrium, at the normal boiling point, delta G is going to be 0, okay? So we can kind of rearrange this equation because what they're asking us for is the normal boiling point. So what part of this equation are they really asking us to solve for here? They're asking us to solve for T, right? So let's rearrange this thing so that we can solve for T. So we've got 0 is equal to delta H minus T times delta S, okay? And you can do this one of two ways. You can plug your numbers in first if you want to. and then you can solve for T. I prefer to solve for T first and then plug all my numbers in. That's just my way of doing it, but again, if it works better for you, if you like to just plug in all the numbers first and then, you know, solve for the variable, that's okay too. But if we were going to do that, we'd end up with negative delta H is equal to negative T times delta S. And then if I divide both sides by negative delta S here, then I end up with T is equal to delta H over delta S. Okay? Well, how do I know what my delta H and my delta S are here? Okay, so this is one of those where you're going to look in the back of the book and find the data for this. Okay? So on this one, I'm going to cheat a little bit and look at my numbers here in the front of the book. But the delta H for this one, well, okay, here's the other thing. These are not necessarily at, this delta H and this delta S are not necessarily at standard conditions. But the assumption we made yesterday is the delta H and the delta S don't change that much based on temperature. So if we look up the delta H 0 and the delta S 0, then we can assume that we can approximate at least. Okay, it might not be exactly right, but it's going to be close. So what we need to do here is we need to plug in our delta H and our delta S. Okay, now our delta H for this one, it's going to be positive, right, for this phase change from CCl4 liquid to CCl4 gas. And what we have to do to find the delta H is we would have to look up the delta H of formation of the CCl4 gas and the CCl4 liquid. Okay, so the heat of formation of the gas is negative 106.7. I'm running out of room here. I'm going to do this up at the top. Okay, so my delta H for this reaction it's just products minus reactants, right? So the delta H for my product here is negative 106.7. I'll write it down here. Kilojoules per mole. Okay, and then my delta H of formation for the CCl4 liquid is negative 139.3 kilojoules per mole. Okay, now this is a one-to-one stoichiometry, which is nice. We don't have to multiply either of these numbers by anything because we don't have any coefficients. So basically we're just going to take products minus reactants, negative 106.7 kilojoules per mole, and then we'll multiply that by 1. But that's just because there's a coefficient 1 right there. And then we're going to subtract the delta H formation of the products, which is negative 139.3. I don't know why I'm putting the units on this one. I didn't on the last one. So that's going to give us our delta H for the overall reaction that's occurring here. Okay, and so our delta H here, would you expect it to be negative or positive just before we even figure this out? Okay, we have to put energy into this thing, right, to change it from a liquid to a gas, so we would expect our delta H to be positive. It ends up being a positive 32.6 kilojoules. Okay, so there's our delta H. Right, so I'm going to write that down here, plus 32.6 kilojoules. Divided by the delta S. Okay, now we got to figure out the delta S. And again, we would want to look in the back of the book or, you know, online or wherever you can find this information and find the S of, so not even the S of formation, it's just the S of this, the entropy of this particular thing. So the entropy of the liquid is 214.4. 214.4, and you got to pay attention to the units here. This is joules per mole times Kelvin. Okay, and then the S over here for the gas, would you expect it to be more or less than that entropy? Yeah, because it's a gas, right? So 309.4. joules per mole times Kelvin. Okay, so there's our two S's. So then to find the delta S here, we do the exact same thing as we just did. We take products minus reactants. Okay, so that's going to be 309.4 joules per mole times Kelvin minus 214.4. And again, those are both multiplied by 1 because we have a coefficient 1 in front of both of those in the equation. And that should give us, again, a positive entropy change. Does that make sense? Yeah, because we're going from a liquid to a gas, so we would expect the change to be positive here. So it's plus 95.0 joules per Kelvin. The moles went away when we multiplied by the 1 mole in the equation. I probably should be more careful with my units here. I'm just trying to get through this. Well, we got a little bit of a problem here, don't we? What's the problem? Yeah, we need to make sure we have the same units when we plug these in. So I'm just going to go ahead and change this right now to 0.0950. Sorry. Kilojoules per Kelvin. Okay. So then this is going to be plus 0.0950 kilojoules per Kelvin. Okay. And then when we divide those two by one another, you should get, what are they asking us for here? Normal, okay, so normal boiling point, they don't specify whether it needs to be in Kelvin or Celsius. Let's just keep it in Kelvin. So you should get 343 Kelvin, I believe, when you work this out. Okay, so that's your normal boiling point. That's about 70 degrees Celsius. Okay, and again, this is very approximate because we used the delta H at standard conditions and the delta S at standard conditions. You know, obviously this temperature is not exactly at standard conditions; it's quite a bit higher. But that's going to be approximately your boiling point of the CCl4. Okay, so that's kind of how that works. All right, another sample problem here, and I don't think I put the equilibrium arrows on your notes again. Sorry about that. So the Haber process for the synthesis of ammonia, we talked about this one yesterday. This process just comes up over and over again. What we want to do now is we want to calculate delta G at 298 for a reaction mixture that has 1 atmosphere of N2, 3 atmospheres of H2, and 0.5 atmospheres of NH3. Okay, so what we want to do here, we have to calculate the delta G under non-standard conditions, okay? And the reason it's at, why are we at non-standard conditions right now? Is it the temperature? Yeah, the temperature is okay, right? But we have a higher pressure than standard conditions. All right, so what we're going to have to do here is we're going to have to use the equation that we just learned, which is the delta G equals delta G0 plus RT ln Q. Okay, so we're going to have to do a couple of things here. All right, first thing we're going to have to do is we're going to have to figure out what the delta G0 is for this one, for this reaction. Okay, so the way that we would have to do that, is it delta G0 formation? I'm going to have to look in the back of the book and make sure on that. Yeah, it is delta G of formation. So what you can do on this one, actually, because both of these right here, this is N2 and H2, those are elements in their standard state, their most common state. So the delta G for both of these is going to be 0. Okay. Now, when we're calculating the delta G of formation, this is not exactly a delta G of formation, because do you remember how many moles of product you're supposed to make with a delta G of formation or a heat of formation? It's supposed to be 1 mole, right? We're making 2 moles here. Okay, so when I look up this delta G of formation, we're going to have to multiply it by 2. This is NH3 gas. So its delta G of formation is negative 16.66. So when we multiply that by 2, it's going to be... Gotta watch out there, I guess. So when we multiply that by 2, it's going to give us about 33.3, negative 33.3. Okay? Is that better? Okay. So negative 33.3 kilojoules per mole. Okay? Because again, the delta G of formation there is negative 16 point whatever. Okay? So we multiply that by 2, that gives us our delta G for this reaction. Okay? At standard conditions. Alright? So that's this right here. Okay? The R is just a constant. They're telling us the temperature of this reaction. It's 298 K. Alright, so we can just plug in the temperature. We're going to have to figure out Q, though. Alright? So now we got to think back to equilibrium a little bit. What's our Q expression for this reaction? Okay. Right, so you got to watch out for your exponents there because of the coefficients. And since these are gases, we're going to write this in terms of pressure. Okay, it's been a long time since we've done that. So the pressure of the NH3, we're going to have to square that because of the coefficient 2 that's in the equation, right? And we're going to divide that by the pressure of the N2. And that's okay because it doesn't have a coefficient, times the pressure of the H2 cubed. Okay? So they give us all those values in the problem here, so we just have to plug this in now. Pressure of our NH3 is 0.5. And we square that. And again, don't worry about your units here. When you're figuring out Q or K, these numbers become unitless when we plug them in. Pressure of the N2 is 1.0. And the pressure of the H2 is 3.0. And we have to cube that. Okay? So when we work all that out, our Q here should be 9.3 times 10 to the negative third. Okay? So now we have basically all the numbers that we need to finish calculating this problem. Okay, just got to plug it all in. And then we can calculate our delta G at non-standard conditions. Okay, so we plug this in, delta G equals, and another thing we're going to have to watch for here is make sure all of our units are okay. All right, here's the trick on this one, and this is not fun. What unit does R contain? I don't know if I should make that singular or plural. Okay, let's look back at our R here, right? This is in joules per mole times Kelvin. Well, that's a problem because we just calculated our delta G in kilojoules, right? So I think rather than, well, yeah, I don't know. I mean, our final delta G, we probably want it to be in kilojoules, so it's probably easier to change this number right here to 0.008314 kilojoules per mole times Kelvin. I know that's annoying. Or you could just say 8.314 times 10 to the negative third. Yeah. Okay, whichever way you prefer to write that. But we've got to make sure that our units match here. Okay? So, again, when we plug all this in, our delta G here is negative 33.3 kilojoules per mole. And I guess really that's just kilojoules at this point because we multiplied it by the moles in the equation, so just kilojoules there. Plus the R, which we just said was 0.008314 kilojoules. Per mole times Kelvin. And then we multiply that by our T, which is 298 K. And then we multiply that by our Q, which is unitless, 9.3 times 10 to the negative third. okay? And so then our delta G for this reaction ends up being, and I guess I could have kept this as kilojoules per mole. Probably if I do that, then everything's going to match up at the end, which is better. So then when we add all that together, you should get a negative 44.9. Good. Kilojoules per mole. Okay? Now, let's just stop and think for a second here. What does that tell us about the spontaneity of this reaction under these conditions? Okay, it's a little more spontaneous going forward than it would be at standard conditions. Does that make sense? So we actually made a change that's going to make this more spontaneous towards the products. Okay? So again, delta G can tell us something about equilibrium. It's kind of just a different way of looking at it. And we could have figured out the same thing thinking about Le Chatelier. Okay? So let's say that we have... Sorry. Okay, we're getting an announcement right now that the internet is down. Alright, anyway, moving on. So, you know, I realized I was going to talk about Le Chatelier there. Let's just move on, okay? The idea is when you understand Le Chatelier, you can basically come to the same conclusion there. That if you are increasing, looks like we're increasing the amounts of the reactants, right? If we increase the amounts of the reactants, it makes sense that would push the equilibrium towards the products, right? And we have 3 atmospheres of H2 here, so we've increased the amount of H2 from equilibrium. Okay, lots of distractions this morning. All right, when in equilibrium, we can actually relate delta G to the equilibrium constant. Okay, so here's the equation we're going to use for that. Delta G 0 is equal to negative RT ln KEQ. All right, so here's how we can do that if you just want to see how that kind of gets derived. If we have our delta G equals delta G 0 plus RT ln Q, right? At equilibrium, what happens to Q? Q is equal to K at equilibrium, right? Okay. Now what happens to delta G at equilibrium? 0, okay? So what we end up with here is 0 equals delta G at standard conditions plus RT ln K, or KEQ, okay? It's equilibrium constant. So then we rearrange that equation, and you end up with delta G 0 is equal to the negative RT ln KEQ, okay? So that's where that comes from. We can also relate that to this equation. Obviously, there's delta G in both of these, so we could take well, that's just inconvenient. This equation ends up being on 2 lines. Here, I'm just going to take it from here. We can substitute this in for the delta G 0, okay? And we end up with this equation down here, which can sometimes come in handy. So, I believe this is the equation that you get on your equation sheet. And you also get this equation, okay? So, I mean, it doesn't take a lot to figure out how to rearrange those so that this is equal to that, and you might need that every once in a while, okay? And when you would need that is if they don't give you any delta G information in the problem, but they have given you delta H and delta S information, and they ask you to relate that to the equilibrium constant, okay? Then you might use this bottom equation rather than the one with the delta G in it, okay? If we need to solve for the equilibrium constant, and I believe, I'm not entirely sure, but I'm pretty sure that they give you this equation too. I'm going to have to check on that, and then we can talk about it in class. But basically, all you're doing here, I mean, if you got a natural log, right? Remember, the way we get rid of natural logs is to E everything, okay? So if you're rearranging this, we want to get the ln KEQ on a side by itself, okay? And that's going to be equal to the negative delta G0 over RT, right? Does that make sense, what I just did? Okay, so then to get rid of the natural log here, you just E both sides of this thing, okay? And so then what you end up with is the KEQ is equal to the E, the negative delta G over RT, okay? So this whole thing right here just becomes the exponent with the base E, okay? So that can come in handy sometimes if they ask you to solve for the equilibrium constant when they give you the delta G, okay? All right, so how delta G 0, no, sorry, how delta G, this 0 shouldn't be here and I can't erase it now because it was on last year's notes and I shouldn't have put it there. All right, so how delta G, well, wait a second, maybe I changed my mind there. Yeah, I guess that is delta G 0. I knew what I was talking about. Okay, so we can look at, the point here is we can look at the thermodynamic data in the back of the book and you can actually figure out how these two things are related to one another, just based on the information that we have at 25 degrees, okay? If the delta G0 is negative, then at those standard conditions, then the equilibrium constant is going to be greater than 1, okay? Well, now what does that mean if the equilibrium constant is greater than 1? It's product favored, right? Okay, so that means, another way of saying that is, it's spontaneous in the forward direction, okay? So you see how these things are kind of all fitting together? Okay, if delta G is 0, then the equilibrium constant is equal to 1, okay? Which means that we're in this perfect equilibrium, okay? If the delta G0 is positive, then that means the KEQ is less than 1, okay? And so then it's going to tend to be spontaneous in the reverse direction, okay? Which means it's going to tend to be reactant favored rather than product favored, okay? So that's kind of the idea there. So, use the standard free energies of formation to calculate the equilibrium constant at 25 degrees for this reaction. Again, we just can't get away from this reaction here. So for the reaction involved in the Haber process, so we've got N2 plus 3H2 yields 2 NH3 again. And we want to calculate the equilibrium constant here. All right, so probably the equation we're eventually going to want to use, now we may not be able to use this right off the bat, is the E to the negative delta G0 over RT, okay? And actually we probably can just use this equation as long as we can figure out what the delta G0 for this reaction is, right? So we actually figured this out already, didn't we? The delta G0 for this reaction. We figured out, if you look back here, where is it? There we go. Negative 33.3 kilojoules per mole. Okay? So we don't have to do any refiguring there, which is kind of nice. So the delta G0 for this reaction is negative 33.3 kilojoules per mole. Okay? Now again, we're going to have to fix one of these two numbers. Either we fix our R or we fix the K. Right? Now, in this case, it doesn't really matter because we're not trying to solve for a delta G, so we don't need our number to be in kilojoules at the end anyway. We just need to make sure these two match up. And I prefer bigger numbers to smaller ones. I don't know if you guys agree with that. So I'm actually going to change my delta G this time to be negative 33,300 joules per mole. Okay? Because to me that's just a little bit nicer than having to work with a very small r here for my decimal. Okay? So this is basically going to be e to the negative 33,300 joules per mole divided by, this gets a little messy here, 8.314 joules, what is that unit? Joules per mole times Kelvin, I think. Times our temperature, which we're trying to find our K at 25 degrees, right? So at 25 degrees, that's 298 K. Okay? And so what I would do is I would solve for all of this stuff in the exponent first, right? And then take e to that power, okay, whatever it ends up being. And so when you do that, I think that when you divide these, it ends up being 13.4. Is that about right? 13.4? Okay. So basically what you're going to do then is e to the 13.4 power when you punch it into your calculator, okay? And that should give you your equilibrium constant for this reaction. Okay, let's make a prediction first. The delta G for this reaction is very, very negative, right? Can we agree on that? So what would we expect the size of our K to be here before we even calculate it? Yeah, probably a lot bigger than 1. This is going to be very product favored, right? Okay, so what we end up with, you know, and you might have already calculated the number, but 7 times 10 to the 5th or so, okay, for your KEQ. So that's kind of how you do that, okay? Now is that the last? Yep, that's it. Okay, so that kind of hopefully explains how the delta G is related to the K, and again, you have these equations on your equation sheet, so most of the time it's just a matter of plugging it in. Okay? All right, have a good spring break, everybody.